In this video, we're going to examine in more detail this evaluation map phi sub square root of 2 from q bracket x to q adjoin the square root of 2. So once again, q adjoin square root of 2 is the set of all numbers of the form a plus b root 2, where a and b are rational numbers. And once again, I claim that q adjoin root 2 is a field. I'm not going to prove that right now, just take my word for it. Alright, so let's take a look at the map phi sub square root of 2. I want to ask the following question. What is the kernel of this map? Okay, so let's first recall that phi sub square root of 2 of any polynomial is that polynomial evaluated at the square root of 2. So that means that for p of x, for a polynomial p of x in q bracket x, to belong to the kernel of this map, we need p of the square root of 2 to equal 0. Okay, now here's a fact. No linear polynomial p of x will have this property. For if it did, then we'd have p of x equal to a naught plus a1x for some rationals a naught and a1. Okay, and that's going to cause a problem for us because then we're saying that p of square root of 2 is equal to 0, which would mean that a naught plus a1 root 2 is equal to 0. But then if we solve that equation, we would get square root of 2 equals negative a naught over a1. And that's impossible because both a naught and a1 are rationals. So a naught, negative a naught over a1 is also rational. Okay, so there's not going to be any linear polynomial in the kernel of this homomorphism. Okay, but can we think of a quadratic polynomial that would be in the kernel? The answer is yes. It does have a quadratic polynomial. One such quadratic polynomial is x squared minus 2. All right, and here's why that polynomial is in the kernel. If p of x is equal to x squared minus 2, then evaluating that at square root of 2 gives me square root of 2 squared minus 2, which is 0. Okay, so the evaluation map at square root of 2 takes this polynomial to 0. That's phi sub square root of 2. So that means x squared minus 2 is in the kernel of this map. And at this point, I'm going to claim that the kernel of phi sub square root of 2, not only does it contain x squared minus 2, this kernel, it is an ideal, and that ideal is exactly the principal ideal generated by the polynomial x squared minus 2. All right, here's a quick proof. If q of x does belong to this principal ideal, then that means that q of x is a multiple of the polynomial x squared minus 2, a polynomial multiple. So it's equal to, I'm going to call it d of x times x squared minus 2 for some polynomial d of x in q bracket x. All right, so that means phi at square root of 2 of that q of x, because I'm trying to verify q of x is in the kernel of this map. If I take the evaluation homomorphism at root 2, apply that to q of x, then I get q of square root of 2, which is the same thing as d of root 2 times root 2 squared minus 2, because I'm just taking this polynomial here, evaluating that at root 2. And that gives me 0 because this factor here evaluates to 0. Okay, so that means q of x does belong to the kernel of phi sub root 2. Okay, that part is complete. So I can further say this principal ideal generated by x squared minus 2 is a subset of the kernel. Good to know. Okay, now I'd like to prove the converse. All right, so we're going to start a new argument, and we're going to try and prove that the kernel of phi sub square root of 2 is a subset or subideal of the ideal generated by x squared minus 2. All right, so new argument. Let's suppose, and I'm running out of good polynomial symbols here. This is the tricky part about writing one of these. I'm going to use m of x. Why m? I don't know. It's a letter I haven't used yet. Suppose m of x belongs to the kernel of phi sub square root of 2, and we will prove that x squared minus 2, this polynomial, divides m of x. All right. So to do that, we're going to use a strategy that's commonly used in number theory when we're trying to prove that one thing divides some other thing, and that is we're going to use a division algorithm to divide this by this, get a quotient and a remainder, and prove the remainder is 0. That would prove that this divides this thing. Okay, so to do this, let's use the division algorithm. We have m of x equals x squared minus 2 times some q of x plus r of x for some polynomials q and r such that the degree of r of x is smaller than the degree of the thing that we were dividing by, and that degree is 2. All right, so we can get a quotient and a remainder, and the remainder is linear or smaller. That's going to be crucial here. All right, so what do we know? So we have m of x is in the kernel of this map. So in other words, m at the square root of 2 is 0. That's what it means for m to be in the kernel. And also, if I look at this chunk of my polynomial, let's just box out things that we know are going to evaluate to 0 at square root of 2. So that's 0 at square root of 2. And then this piece here also is going to be 0 at square root of 2 because that factor right there is 0 at x equals the square root of 2. Which means this piece here also has to be 0 at x equals the square root of 2 because everything else in this equation is. So since x squared minus 2 times q of x is also 0 at x equals root 2, because that is true, r of root 2 has to equal 0. All right, but what did we just establish earlier? We said that no linear polynomial over the rationals is going to satisfy this. So r can't be linear. And it also can't be a non-zero constant because a non-zero constant will never evaluate to 0, no matter where you evaluate. So it can't be a non-zero constant. So what's left? A 0 constant. That's the only thing that's left. If we're less than quadratic, can't be linear, can't be a non-zero constant, that means that r of x has to be just the 0 polynomial. Okay, so therefore, m of x is equal to x squared minus 2 times q of x, and that's that. So x squared minus 2 divides m of x, and so m of x belongs to the principal ideal generated by x squared minus 2, and that proves the other half of my argument, because I assumed m of x belonged to the kernel of phi square root of 2, and now I know it belongs to this principal ideal. Therefore, and now we're about to reach the climax here, therefore, the kernel of the evaluation map at square root of 2 is exactly this principal ideal. Okay, why did we go to all this trouble? How much did we write here? This feels like we did a whole lot here. Yeah, a whole lot. Okay, so we started here and we're trying to figure out what exactly is in the kernel of the evaluation map at square root of 2. Now we know the answer to that question. The kernel of the evaluation map at root 2 is exactly the set of polynomials that are multiples of x squared minus 2. Now, we're going to pull in the first isomorphism theorem. By the first isomorphism theorem for rings, there we go. By the first isomorphism theorem, we know that the original ring, which was q adjoint x, q bracket x, the polynomial ring over the rationals, modulo the kernel of this map, which is the ideal generated by x squared minus 2. This is isomorphic to the image of the map phi sub square root of 2. What is the image of that map anyway? Well, if p of x is equal to a plus bx, I'm just using a simple linear polynomial, then phi at square root of 2 of p of x is equal to a plus b root 2. So this is just a fancy way of saying that this phi sub square root of 2 can hit every element of q adjoint root 2. So everything in q adjoint root 2, remember that's the set that we defined up here, q adjoint root 2 up in your upper left, everything in q adjoint root 2 is in the image of phi sub square root of 2. And in fact, every element there could have been gotten in some more creative way. Like if you'd said, okay, think of a polynomial, for example, that gives me, I don't know, I'm just going to write something down here, that gives me 3 plus 2 root 2. Well, I could have said, how about the polynomial p of x equals 3 plus x cubed? If I evaluate that at square root of 2, I'm going to get 3 plus 2 root 2. Okay, I could have done that. But this is just telling me, well, you could have just used 3 plus 2x. That would have gotten you there. And that's fine. I can get everything in q adjoint root 2 just by thinking about linear polynomials. That q should have like a double back there. There we go. So anyway, the point of all this is the quotient of this polynomial ring by the ideal generated by x squared minus 2 is exactly q adjoint root 2, because that is the image of this map. Everything that this map gives me is going to be some rational plus some rational times root 2. And every number that is expressible as rational plus rational root 2 is in the image of this map, of this phi sub square root of 2. So that means that I now have an isomorphism between this very mysterious quotient ring and this fairly concrete looking field of numbers that consists of rationals and the square root of 2 and combinations of those. That's cool. The fact that I can understand this as just this very nice subfield of the real numbers, pretty profound finding there. Okay, so let me just say one more thing about this, because I want this isomorphism to feel like something real, something we can wrap our hands around. So what is in this quotient ring, q bracket x mod x squared minus 2? One thing we've been finding is if we take the polynomial ring q bracket x and we mod out by a quadratic, then all of our congruence classes end up being of the form a plus bx. So in other words, everything is congruent to some linear polynomial or lower, linear constant, something of degree less than or equal to 1. And we also know that in this quotient ring, the congruence class of x is something whose square is equal to 2. And that's because modulo x squared minus 2, x squared is congruent to 2 modulo that ideal, modulo x squared minus 2. Okay, so I have an element in this ring whose square is basically 2. In the meantime, in q adjoint root 2, I also have an element whose square is 2, namely the square root of 2. Square root of 2 squared is equal to 2. So the link between these two rings, it's not just this mysterious thing that's hidden under the first isomorphism theorem. There's actually an isomorphism that you can see and feel and taste here, and that isomorphism is the one that maps every rational to itself and maps this element x to the square root of 2. So that's what my isomorphism does. It says really, if we're talking about polynomials mod x squared minus 2, you can talk about x, but that x basically behaves like a square root of 2. And that's the link between those.